We're going to talk about uncertainty and variability and detection limits. Our learning objectives for today are to relate the concepts of uncertainty and variability to confidence intervals and prediction intervals, to calculate instrument detection limits and method detection limits using standard methods and concepts of statistics. And third is to understand how many significant figures to report from laboratory data. All right, so we talked about the concepts of variability and uncertainty, but regarding variability and prediction, consider the following. If we had a perfect sensor, right, some magical sensor that detected the exact concentrations of water quality constituents at all times of the day and throughout the entire year, we would see that those concentrations would change just naturally in a water source. So if it's a river, they're not going to stay constant. They're going to fluctuate up and down, right? So this is what we would refer to as the variability of the population. If the population is the entire volume of water that flows through a river past a certain point, then that's going to be variable. You're going to have fluctuations throughout the day, throughout the week, throughout the year. We measure variability using the statistic standard deviation. And understanding the variability of a system can help us to predict what types of values we might anticipate from future samples that we collect. And this range of probable values for future samples, this range is known as a prediction interval. All right, so you may have seen this before in your statistics class, but if we have the distribution of the entire population, which we will never know, right, because we don't have a magical sensor to know how that concentration is going to fluctuate at all times of the day. But if we did have that distribution, then the center of it would be the true mean of the population, which we'll never know, but we're going to try to make inference about. And then if we take one standard deviation away to the left or to the right, that gives us the first prediction interval, which is where you'll find 68% of the values in the population. Now, this is for a normal distribution, and most environmental contaminants are distributed normally, or they might be distributed log normally. We're going to get into the difference between normal and log normal is going to come in a future reading assignment. But so you have, you take the standard deviation away, one standard deviation. If you take two standard deviations to the left and two standard deviations to the right, that interval right there includes 95% of the values in the population. So 95% of the values that you might obtain from future analyses. And then if you take three standard deviations, you'll have more than 99% of the values. All right, so that's variability and prediction. The second concept to contrast with that is uncertainty and confidence. Okay, so like I mentioned, if we had a magical sensor and we could know exactly what this population distribution is, we could determine what the exact true mean of the population is. But we don't have that magical sensor, so we'll never actually know what the true mean is. We can only know what the mean from our samples are, which is taking into account some uncertainty that we will always have, just because samples have limitations, right? We can't analyze the entire volume of water in this lake. We can only analyze a sample. So it's impossible to measure the exact mass of pollutants in all of the water, but we collect samples, we analyze them to gain insight, and in other words, make inference about what that true value might be. And this is what we call the confidence interval. So uncertainty describes our lack of knowledge about the true value of the mean or some other parameter. But the best we can do is express how much confidence we have in that estimate. So you probably have studied in your statistics class the central limit theorem. This tells us that if many people were to collect random samples from the same population, they will all get different values for the calculated average. So let's take our class here today. So there's 14 of you signed on. So if all 14 of you were to go out to San Diego River and over the course of a week collect 10 different samples from the same point in the river, and you analyze those samples for nitrate and you calculate the average value from your nitrate concentrations, each of you are going to get a different mean value. you're sampling from the same exact point, you're collecting samples the same number of times on the same days, but you're all going to get a different average value, and that's just due to randomness. However, your average values, if we were to get more people, so instead of 14, let's say we got 1,400 people to do the same thing, and we plotted those values on an axis, on an x-axis, like a histogram, we would see that the values would follow a normal distribution, and the mean would be equal to the true population mean. So that's what the central limit theorem is. So the more times you collect samples, the averages from each of those statistical samples will follow a normal distribution. This theory right here allows us to calculate what's known as a confidence interval. And that tells us the probability that the true mean of the population is within a certain distance of our calculated sample average. So I just want to re-emphasize that point. I'm going to repeat. The prediction interval tells us the probability that a future measurement will appear within some range. So 99% of the values appearing between this range, mean minus 3 standard deviations and mean plus 3 standard deviations. That's not the same thing as a confidence interval. A confidence interval tells us the probability that the true mean of the population is within a certain distance of our calculated sample average. Let's look at some other visualizations to further understand this concept. So again, let's say instead of 15 or 14 people, let's say we have 20 people in the class. All right, if we have 20 different people collecting samples of nitrate from San Diego River, and you each collect, let's say, 30 samples, and you calculate the average of those 30 samples. All right, so here's person number one. You get an average value that's equal to this. If this is an x-axis, let's say this is like 0 to 10 milligrams per liter. So let's say the first person gets 4.5 milligrams per liter. The second person gets 5.3 milligrams per liter. The third person gets 3.8 milligrams per liter. The fourth person gets 4.9 milligrams per liter, etc. So you all get different average values. But if each of you calculated your confidence intervals associated with those average values, and there's a formula, of course, to calculate the confidence interval, you use the standard deviation. We're going to go through that. And it's also presented in detail in your reading. But if each of you calculated your confidence intervals, every one of you would have a confidence interval that overlaps with the true mean population, which is shown here in the center, except on average, 1 out of 20 would have a confidence interval that's either too high or too low. So this 1 out of 20, or 5%, this is what's known as the alpha error. So if we set our alpha level to 0.05, which is pretty standard, then that means on average 1 out of 20 times that you complete this study, you're going to get a misleading result. Now that's different from the prediction interval, which is what's shown here on the right. So the prediction interval says that if you collect, let's look at the 95% prediction interval. If you collect 20 samples of the same sample location, the same river, same analysis, that means that 19 out of 20 of those future values of the samples you collect will fall within this range of concentrations. And 1 out of 20, just by chance, will be outside of that range. Right, so this is prediction interval is referring to each value you get from an individual environmental sample. The confidence interval is referring to the calculated mean or average from all of your environmental samples that you collect, which is referred to as your statistical sample. All right, so I know it's really early to think about statistics and math, but this is a really important concept. So I want to ask first if there's any questions at this point. Between a confidence interval and a prediction interval. Feel free to use the chat if you have questions as well, or interrupt me if you would like me to clarify? Okay, so this is important. This is going to be something you'll see on the exams and quizzes, and it's something that you're going to need to understand when you write up your lab reports. All right, so let's look at the contrast between these concepts, right? Uncertainty versus variability, and confidence versus prediction. So uncertainty is associated with a confidence interval, and a confidence interval tells you the probability of calculating an average value from your sample that includes the true mean value of the population. So if your alpha level is set at 0.05, then your confidence will be 95%. So 95% probability that your calculated average will have a confidence interval that includes the true mean of the population. Variability, on the other hand, is associated with a prediction interval. And a prediction interval tells you the probability of your next sample producing a value in between a given range. All right, and both of these are used in regulatory settings, like, for example, the State Water Board or the EPA. Both of these concepts of variability and uncertainty are used when determining thresholds for compliance. And this example problem will illustrate that. So let's suppose that you're managing a wastewater treatment facility and your facility has a discharge permit that specifies the following. It specifies that your mean annual concentration of TSS in the effluent must be below 50 milligrams per liter. And it also specifies that the TSS concentration on any single sample cannot exceed 75 milligrams per liter. So you've got two different thresholds to which you're going to compare the calculated values from your samples. The first one is an average, and the average needs to be below 50. The second one is any single sample, and it needs to be below 75. So let's suppose for this treatment facility, you're evaluating two processes, and you're not sure which process will be the best to use. So you conduct, a short-term study, and you want to say, okay, let's see what the performance of process A is at reducing TSS, and let's see how process B compares to that. All right, so you collect 52 samples. Let's say you do this over the course of a year. You collect samples every week, and you calculate from those 52 samples, you analyze TSS, and you calculate the average concentration, and you calculate the standard deviation. You could also, the standard error is related to the standard deviation in the sample size. All right, so that's all covered. How to calculate those, that's all covered in your reading assignment. But here's the results from your study. Let's suppose process A produces an effluent with a average concentration of 44.5 milligrams per liter, and process B produces an average concentration of 40.1 milligrams per liter. So let's do a quick poll. I'm going to set up a quick poll here. All right, so I just launched a poll. You should be able to see it. I want to know, given the information you have right now, there's no right or wrong answer. We haven't finished the example yet, but which process do you think is the better process? I got 12 out of 14 people have voted. 2 people. All right, 13 people, just missing 1. All right, we got all 14 votes. So let's share the results. All right, most of you said process A, but some of you said process B. All right, so with this information right here, it might, at first glance, it might look like process B is a pretty good choice because you have a lower concentration. Both of them are below the sample average, right? 50 milligrams per liter. But a lot of you said process A, and let's figure out why. Why is process A potentially the better choice here? Well, if we look at our confidence level and we calculate the confidence interval, the 95% confidence interval, we can then see that for process A, that interval goes from 43 to about 46 milligrams per liter. For process B, it goes from 35 to about 45 milligrams per liter. All right, so the confidence intervals, not even just the average, but the confidence intervals for both processes are still below that threshold of 50 milligrams per liter. So in terms of the first threshold, both of these processes are complying. However, if we look at the prediction interval, and again, we'll use a 95% prediction interval, the calculated lower prediction limit and the calculated upper prediction limit for process A goes from about 34 to about 55. For process B, it goes from about 4.4 to about 76. And that is directly related to the fact that process B has a much higher standard deviation than process A. And I'm assuming that's probably why those of you who chose process A did so, because you saw the standard deviation. And you were correct if that was your line of thought, right? So process B has the upper prediction limit of 75.8, which is exceeding that second threshold of any single sample not exceeding 75. On the other hand, process A, the upper prediction limit is still quite a bit lower than 75, so you can have much better a much better assumption that process A will comply not only with the first threshold, but also with the second threshold. All right. Now let's talk about detection limits. So a detection limit is it's defined as the lowest quantity of a pollutant that can be reliably measured in a sample and distinguished from a sample with an absence of that pollutant. So we have two different types of detection limits that can be calculated. The first is an instrument detection limit. And the way that we calculate the instrument detection limit is by analyzing 7 instrument blanks and calculating the upper limit of the 95% interval of the average of those readings. That's using the normal Z value. So this is defined in the standard methods book of water and wastewater analyses. And in the previous lecture, I talked about instrument blanks. That lecture is one of the recorded lectures that you have. So calculating 7 instrument blanks and then getting the upper limit of the 95% interval. The method detection limit is calculated by analyzing 7 process blanks. So the difference between an instrument blank and a process blank is that an instrument blank, you're just putting, let's say, DI water as a blank. You're putting that directly into the instrument to get back the reading that the instrument provides. The process blank, on the other hand, you are concentrating, you're processing, you might be doing an extraction. You're going through this whole process before you actually put the sample into the instrument. So the way we calculate the method detection limit is by analyzing 7 process blanks and getting the upper limit of the 99% interval using a t-distribution. So 2 different methods, but 2 different limits that typically need to be reported when you are working with a laboratory. So let's see an example here. This is all part of your assigned reading, but let's suppose that we have the following results from 7 instrument blanks. All right, so what is the instrument detection limit at 95% confidence? And if you take a look at the reading, this example is available as an Excel spreadsheet, so you can see how the calculations are performed. So we start by calculating the standard deviation of those 7 blanks. So we get the 7 values in Excel. The formula looks like this, and you get a value of 0.77. Then we use the normal distribution with a probability of 95%. And Excel, the function is norm.s.inv, and that gives a value of 1.645. Next, we calculate the average of those instrument blank readings. So using the function average, we get a value of 0.3. And finally, we use the formula for confidence interval to get the upper 95% limit. And that's by taking the standard deviation, multiplying it by the inverse of the normal distribution, and then adding to that the sample average. So 0.77 times 1.645 plus 0.3 equal to 1.6. That would be the instrument detection limit. The method detection limit, again, we analyze process blanks. Let's do an example here. So suppose we have the following results from 7 process blanks that were analyzed, and we need to calculate the method detection limit at 99% confidence. So it's pretty similar procedure. The one difference is that in the standard methods, it requires you to use the t inverse instead of the normal inverse. And we use it at 99% instead of 95%. So standard deviation, you calculate that from all 7 samples. You calculate the inverse of the t distribution. Here you have to specify the probability, 99%. You also have to specify how many degrees of freedom. So degrees of freedom is the sample size, 7. So here you have 7 process blanks minus 1. And so that gives a value of 6. So use this function in Excel, t.inv, and that gives you a value of 3.143. Calculate the average of the process blank readings and then use the same formula as shown in the previous example to get the upper limit, which in this case is equal to 5.7. So that's your method detection limit. All right, let's talk about significant figures. So for measurements on instruments that give live readings, so you might have instruments that are giving you live readings, kind of like the scale that some of you used in your first lab. You might also have instruments that give you a single reading. So you put the sample in, you press analyze, and then it gives you a number, a single number. So 2 different approaches that we use to determine how many significant figures to report from those 2 different types of instruments. So for those instruments that give live readings, what we want to do is look for the number of stable digits provided. So let's suppose that we're measuring the mass of a sludge sample using a precision balance, right? This gives a live reading. And we just look at the number of digits and we see how many digits remain stable. So if the balance starts out at 1.3537 grams, but then the reading jumps down to 1.3534, jumps back up to 3539, and then back down to 3536, the number of stable digits is 3 after the decimal point. So we should report that value as 1.353. If it's straddling between 3 and 4, then you would stick with the 353 or 354. Like let's say it goes above 1.354, you would stick with the one that is the closest to what the majority of the readings have shown. For instruments that do not give live readings, what we would want to do is use kind of a similar approach to what was described previously with the detection limit. But in this case, we'll take 7 measurements of the same sample, calculate the standard deviation. Let's call that S sub B, the standard deviation. If we multiply S sub B by 3, that will give us 1/2 of the 99+% prediction interval. And so that's going back to that concept of prediction interval where if you start at the mean and you take +3 standard deviations and -3 standard deviations, you have an interval that has more than 99%. So if we multiply the standard deviation by 3, we get 1/2 of that interval. So if we subtract that 3 times the standard deviation from the value that we want to report, so if we want to, whatever value that we are interested in reporting, we subtract 3 times the standard deviation from that, and then take note of how many digits remain the same between those 2 numbers. Then add 3 times the standard deviation to the value that we want to report, and again, take note of how many digits remain the same. And then you just report however many digits remain the same after doing those 2 calculations. Plus, you can report 1 additional digit. This is a little bit abstract. It's going to make more sense if we see it in an example problem. So here's example 4.4 from your assigned reading. When we're using methods that require the use of a machine where we don't get a live reading, right? Like a spectrophotometer sometimes is like this. So we're going to have an example. Let's suppose that we took a reading of the same standard sample 5 times. Instead of 7, in this example, we used 5. Okay, so let's determine how many significant figures should be reported for the single reading. So we calculate the average, and if we get the average of these 5 readings, we get 3.21582,000. The standard deviation from those 5 readings is shown here, and the digits would go on forever if we didn't round. I'm showing a lot of digits just so that you can see how this method works. All right, so again, we use the prediction interval to determine how many significant figures here. If we add 3 standard deviations to the average value, so we take this standard deviation, we multiply it by 3, and then we add it to this average of 3.21582, we will get an upper limit that's equal to 3.2165996, etc. If we subtract 3 standard deviations from the average value, we'll get the lower limit, which will be equal to 3.21504, etc. So you compare these two numbers, and you can see that the digits that remain the same are 3.21. So based on the method presented in the slide before, we can report 3.21 from our average value right here, 3.21. We can report 3.21 plus 1 additional digit. And so that additional digit would be 5. However, since we have 8 following that, we would round that up to 6. Therefore, the appropriate way to report significant figures for this machine would be to report this as 3.216.